Okay. Kinetics and equilibrium, page 216 in the notes. So what we need to do is take a look at the potential energy diagram and look at how a catalyst will alter the PE diagram. I want to add arrow 5 here. So let's just go through, based on our prior knowledge, fill in what each of these arrows represent. So arrow 1, PE of the reactants. Arrow 2 starts at the x-axis, ends at the peak, so it's the PE of our activated complex. Arrow 3 starts at the reactants platform and goes to the peak, so that's our activation energy. Arrow 4 starts at the products platform, ends at the reactants platform, so that is our delta H. And the newly added arrow 5 starts at the x-axis, ends at the products platform, so we would say PE of the products. Okay, so this is our regular reaction pathway. So this would, since it's the normal or the traditional, we would say uncatalyzed. So our uncatalyzed reaction. Okay, so now we add a catalyst to this reaction, and like that, those two mountainside homes, whether you take the traditional pathway or the expansion bridge, where you start and end, so at the start at the reactants, end at the products, you still start and end in the same place, but it's a shortened pathway. So the catalyst is represented by a dotted line, but we're going to create a smaller hill. The shortened pathway starts at the reactants platform, ends at the products platform. It still creates a hill, but it's a smaller hill, a shortened hill, an alternate pathway. So where I just put that dotted line, that would represent the catalyzed reaction. Okay? So now, taking a look at our drawing here, okay, when you take a look at what the catalyst changes in your picture, which arrows has their length been changed? So I noticed that arrow 2 has definitely been shortened, and arrow 2 represents the potential energy of the activated complex. So the catalyst, it decreases the PE of that activated complex. And I also notice that arrow 3's length has also been changed. It becomes much shorter. So arrow 3 represents the activation energy. So I see a decrease in the activation energy with the presence of the catalyst. So decreasing the PE of the activated complex, needing less energy supplied by the reaction. I have this shortened pathway. This makes this a faster reaction. Now, taking a look at what the catalyst does not affect. Arrow 1's length did not change. That's the PE of the reactants. So it does not affect the potential energy of the reactants. I noticed that arrow 5's length did not change, and arrow 5 is the PE of the products. And then I also noticed that arrow 4's length did not change. And arrow 4 is the difference between the PE of the reactants and the PE of the products. So it makes sense its arrow's length was not altered. So the delta H. So the starting and ending position does not change, but the kickstart and making it a faster reaction does change. A great example of a catalyst are the enzymes in your body. Okay, so the enzymes in your body for digestion, so it increases the rate of digestion merely by being present. It decreases the activation energy and the amount of work your body does. And here's the other neat thing. Remember, the enzymes they're present but they don't participate. So here's another neat fact about that, is that when the digestion is finished, your body can recollect those enzymes and save them for the next digestion process. So enzymes, they can be recollected and reused for future reactions. So they can typically be used over and over.